the page fault. Recall that with TLB misses, we have two types of systems: hardware managed TLBs, where the hardware looks in the page table to find the desired translation, and software managed TLBs, where the OS does. In either type of system, if a page is not present, the OS is put in charge to handle the page fault. So whether it's hardware or software managed TLBs, the OS is put in charge to handle the page fault. Again, the page fault are the is what we call if the operating system could not find the page in our memory, therefore but can be found in the disk. The appropriately named OS page fault handler runs to determine what to do. So the OS page fault handler run to determine what to do. Virtually all systems handle page faults in software, even with a hardware managed TLB. The hardware trusts the OS to manage this important duty. So even if it's a hardware managed TLB, we still use an OS to handle this page fault. So it's kind of like trapped into the OS in that page table of the OS we discussed in the first few videos. So here's an example of hardware managed TLB, a page fault control flow. So we define VPN equal virtual address and VPN mask greater than shift, then success comma TLB entry equal TLB lookup VPN. If success equal true / TLB hit. If can access TLB entry that protect bits equal true. Offset equal virtual address and offset mask. Physical address equal TLB entry dot PFN less than shift or offset. Register equal access memory argument physical address else raise exception protection fault else TLB miss. PTE address line 11 equal line 11 PTE address equal PTBR plus VPN times size of PTE. Line 12 PTE equal access memory argument PTE address. Line 13 if PTE that valid equal false. Line 14 raise exception segmentation fault. Line 15 else. Line 16 if can access PTE that protect bits equal false. Line 17 raise exception argument protection fault. Line 18 else if PTE that present equal true. Line 19 assuming hardware managed TLB. Line 20 TLB insert argument VPN comma PTE that PFN comma PTE that protect bits. Line 21 retry instruction. Line 22 else if PTE that present equal false. Line 23 raise exception page fault. If page is not present and has been swapped to disk, the OS will need to swap the page into memory in order to service the page fault. So if page is not present and has been swapped to disk, the OS will need to swap the page into memory again if it's in the disk in order to service the page fault. Because remember, if those have been running in memory before and swap out to memory to free up space in memory or in physical memory, it needs to the OS needs to get that program back from disk to memory to run it again. Thus, a question arises: how will the OS knows where to find the desired page In many systems, the page table is a natural place to store such information. Thus, the OS could use the bits in the PTE normally used for data, such as the PFN of the page for a disk address. So how will the OS knows where the program is in the disk? The answer is the OS could use the bits in PTE normally used for data, such as the PFN of the page for a disk address. So the OS will use the page address it will use the PFN, sorry, it will use the bits in the PTE normally used for data, such as the PFN, to find the disk address to locate that program. When the OS receives a page fault for a page, it looks in the PTE to find the address and issue the request to disk to fetch the page into memory. So if it's an if-else statement, if the OS receive a page fault, like it receive an exception, meaning the page is not in memory, it will look in PTE or page table entry to find the address and issues the request to disk, or to that disk address got from PFN of the PTE, or bits of PFN from the PTE, to get the disk address and issues the request to disk to fetch it back into memory. When the disk I/O completes, the OS will then update the page table. So after the disk I/O completes, after the transfer from disk to memory, the OS will then update the page table to mark the page as present. It will mark the page table, or sorry, it will mark the it will update the page table to add an information that that page is now present. It will update the PFN field of the page table entry, and then it will update the page table entry, or the PFN field of the page table entry. So again, we get the disk address from the PFN from the PTE, and we also update the PFN after we transfer the disk to memory. We also update the PFN field of the page table entry to record the in-memory location. So the reason why we are updating the page table now instead of locating the page in the actual disk is to record the in-memory location of the newly fetched page and retry the instruction. So the retry instruct, because the reason why we need to see it where it is located in memory is because once we retry the instruction, we need those meta information to be able to run it properly in memory, or to manage it in memory. This next attempt may generate a TLB missed, which will then be serviced and update the TLB with the translation. So that first update from disk to memory and then retry instruction will be a missed, and then it will update the TLB with the translation. One could alternately update the TLB when servicing the page fault to avoid this step. So you can simultaneously update the TLB while you are servicing the page fault, like swapping the disk or waiting for the I/O to complete, or swapping the page or disk address from the disk to memory. To avoid this, it's just an if-else statement code. Finally, a last restart would find the translation in the TLB and thus proceed to fetch the desired data or instruction from memory. Again, finally, a last restart would find the translation in the TLB and thus proceed to fetch the desired data or instruction from memory at the translated physical address. Again, finally, a last restart would find the translation in the TLB and thus proceed to fetch the desired data or instruction from memory at the translated physical address. So once it's saved in TLB, it will now run as normal. It will proceed whether it's fetching the desired data or instruction from that page at the translated physical address. So basically running that process. Note that while the I/O is in flight, the process will be in block state. Thus, the OS will be free to run other ready processes while the page fault is being serviced. So the OS could alternately run in memory other processes while the swapping of the page from disk address to memory are being done. Because I/O is expensive, this overlap of the I/O page fault of one process and the execution of another is yet another way a multi-program system can most effective is yet another way a multi-program system can make the most effective use of its hardware. So since you can also do this in your processor, you can execute one while waiting for the other, or like once it's swapping the or in a block state, you can choose to run other processes in memory, and then the furthest out processes in the future could go to the disk for a moment. For a while. Aside, why hardware doesn't handle page faults? We know from our experience with the TLB that hardware designers are loath to trust the OS to do much of anything. So why do they trust the OS to handle the page fault? There are a few main reasons. First, page faults to disk are slow. Even if the OS takes a long time to handle a fault, executing tons of instructions, the disk operation itself is traditionally so slow that the extra overheads of running software are minimal. Second, to be able to handle a page fault, one reason is that first reason is that since the I/O is already slow, there is no reason to optimize it via hardware. So that minimal intervention of software does not matter because the I/O is slow to begin with. Second, to be able to handle a page fault, the hardware would have to understand swap space, how to issue I/Os to the disk, and a lot of other details which it currently doesn't know much about. So it also has to understand the swap space on the disk, which is has to learn like the present protection reference bit that we have discussed. Thus, for both reasons of performance and simplicity, the OS handle page faults and even hardware types can be happy. What if memory is full? If the process described above, described above, you may notice that we assume there is plenty of free memory in which to page in a page from swap space. Of course, this may not be the case. Memory may be full or close to it. Thus, the OS might like to first page out one or more pages to make room for the new pages the OS is about to bring in. So, a lot of times the memory is so full that you don't have a space to swap or get page from disk and then swap it to the current memory. Sometimes you don't have a leeway for that, and therefore the OS needs to swap out first some unused or any furthest out process from now that won't likely be used in the future. The process of picking a page to kick out or replace is known as the page replacement policy. So this we will dig we will gonna dedicate an entire chapter just for this policy. So basically, how do we decide how to page out pages? So that's the key that the key is the one I mentioned, which is the swapping out furthest out process in the future. As it turns out, a lot of thought has been put into creating a good page replacement policy, as kicking out the wrong page can exact a great cost on program performance. Making the wrong decision can cause a program to run at disk-like speeds instead of memory-like speeds. So the reason why we will dedicate a chapter and is because it could be dangerous or cause system altering if you swap out pages that are currently needed by the system, such as the display process. Thus, such policy is something we should study in some detail. Indeed, that is exactly what we will do in the next chapter. For now, it is good enough to understand that such policy exists built on top of the mechanisms described here. Page fault control flow. Page fault control flow. With all of this knowledge in place, we can now roughly sketch the complete control flow of memory access. In other words, when somebody asks you what happened when a program fetches some data from memory, you should have a pretty good idea of all different possibilities. See the control flow in figure 21.2 and 21.3 for more details. The first figure shows what the hardware does during translation, and the second what the second figure shows what the hardware does during translation, and the second what the OS does upon page fault. So these are the two things that's happening during this page fault. So for OS, this is the algorithm or the code for that. So PFN equals to find free physical page. If PFN equals -1, no free page found, PFN equals to evict page. So this is the replacement algorithm. So we will gonna evict process that is furthest out in the future, and then this grid PTE dot disk address comma PFN. So this is how we read how we get the PFN of from the PTE of the disk address of the page of the swap space we want to take out from the disk and put into memory. We update the page table, so PTE.present equals to true. So this is also how earlier where we used the PTE and the PFN value of that to update the PTE to make it a present. Now then PTE.pfn equals to PFN, so present / translation. So this is the line 6, so another way to we update the page table pte.present equals to true, and then we update the pfn, just like what we did earlier when we update the pfn using the pte, because we update that for us to be able to track that it is now present, and then we retry the instruction. So basically that's just the code that we mentioned earlier. So these are the code that we have discussed for hardware control flow algorithm. It's still the same as when we have the OS, because this thing, this translation and then this algorithm by the OS is happening at the same time upon page fault. From the hardware control flow diagram in figure 21.2, notice that there are now 3 important cases to understand when a TLB miss occurs. So this only happen when TLB missed. Again, you only ignite or trap into this page fault if it's not in TLB. So again, this is the hierarchy: the TLB first, and then we check the memory. If it's not in memory, we check on disk. So this is the page fault. So there are 3 cases to understand when a TLB miss occurs. First, that the page was both present and valid, so lines 18 to 21. So we need to check if it's present and valid. 19, else if pte.present equals true, assuming hardware managed TLB insert vpn, pte.pfn, pte.protect bits 21 retry instruction. In this case, the TLB miss handler can simply grab the pfn from the PTE. Again, in this case, the TLB miss handler can simply grab the pfn from the PTE. Retry instruction, this time resulting in a TLB hit. So if the page is present in memory and if it's valid, the TLB miss handler, or if it missed from the TLB, will just simply grab the PFN from the PTE because it exists in PTE. Remember, we only trap into the page fault if it's not existing in PTE, and then that's where we swap into the disk, trap into this algorithm, disk read pte.disk add comma pfn, and we get that disk address from the PTE. So here we simply grab the pfn from PTE, retry the instruction, this time resulting in a TLB hit. In the second case, line 22 to 23, the page fault handler must be run. So else if pte.present equals to false, raise exception, page fault. So that's the page fault handler. So these are the page fault handler. PFN equals to find free physical page. So if there's a we find first if there's a free physical page in memory, and then if PFN equals to -1, no free page. So if there's a free page, we have a different algorithm because we don't need to run this replacement algorithm. So that those are inside the page fault if it's not valid or it's not present in memory. So the page fault handler must be run, although this was a legitimate page for the process to access. It is valid after all. It is not present in physical memory. So the bits that allow us to see if it's present in disk but not present in memory is the valid bits. So if it's valid, it means that it's on the disk somewhere, it's just not present in memory. Therefore, we will find free page, the OS page fault algorithm If not, no page, we run the replacement policy code. Third and finally, the access could be to an invalid page due for example to a bug in the program, line 13 to 14. If pte.valid equals to false, erase segmentation fault. So this is where the user are asking for some process that do not exist at all. Therefore, we will raise an exception. In this case, no other bits in the PTE really matter. The hardware traps this invalid access, and the OS trap handler runs, likely terminating the offending process. From the software control flow in figure 21.3, we can see what the OS roughly must do in order to service the page fault. So these are the rough code of OS on how to handle the page fault, but we will relax this assumption and then provide examples of real life algorithms or real life page control flow in the next chapter. But here on that diagram on the OS algorithm, first the OS must find a physical frame for the sum to be faulted in page to reside within. If there is no such page, we'll have to wait for replacement algorithm to run and kick some page out of memory, thus freeing them for use here. With the physical frame in hand, the handler then issues the IO request to read in the page from the swap space. Again, with the physical frame in hand, the handler then issues the IO request to read in the page from swap space. So once we run the replacement code and we already have the physical frame or space in memory to swap in from disk, the handler of that transfer from from disk to memory will run and then issues the IO request to read in the page from swap space. So it will issue an IO or block. It will be in block state to read in the page from swap space. Finally, when that slow operation completes, the OS updates the page table and retries the instruction. Again, finally, when that slow operation or IO or block state completes, the OS updates the page table and retries the instruction. Again, it will update the page table. So here we update the page table. So this is our like more on OS part. So the hardware algorithm more on like retrying the instruction with the TL and inserting and then raising an exception, and then OS handles the page fault. Again, the hardware do not handle the page fault even though it's a hardware managed TLB. Again, finally, when that slow operation completes, the OS updates the page table and retries the instruction. The retry will result in a TLB miss, and then upon another retry, a TLB hit, at which point the hardware will be able to access the desired item. So present translation and then retry instruction. When replacement really occurs. Thus far, we've described how replacement occur assumes that the OS waits until memory is entirely full. So again, thus, Thus far, the way we've described how replacement occurs assures that the OS waits until memory is entirely full and only then replaces evicts a page to make room for some other pages. As you can imagine, this is a little bit unrealistic, and there are many reasons for the OS to keep a small portion of memory free more proactively. To keep a small amount of memory free, most operating systems that have some kind of average high watermark to keep a small amount of memory free, most operating system does have some kind of high watermark and low watermark to help decide when to start evicting pages from memory. How this works is as follows. When the OS notices that there are fewer than LW pages available, a background trend that is responsible for freeing memory runs. So if it will track, it will have a low watermark and high watermark um, concept. So if the OS notices that there are fewer than LW pages, then it allocate or it configure from LW pages available a background thread or a daemon that is responsible for freeing memory runs. The thread evict pages until there are HW pages available. So the thread will or the daemon will evict pages until there are high watermark pages available, because if the low watermark are fewer than allocated, it means that the thread or the there's no high watermark pages available. The background thread, sometimes called the swap daemon or page daemon, then goes to sleep happy that it has freed some memory for running processes and the OS to use. By performing a number of replacement at once, new performance optimization become possible. So in replacement policy code, those are handling the replacement when the memory is full, but that's a bit unrealistic. Sometimes you need to always maintain some space for a swap space. So this is where the low watermark and high watermark pages size comes in. So it uses a background daemon to do this process at once. So by performing a number of replacements, or instead of running that replacement algorithm, if the memory is full, so since we use the high watermark and low watermark, new performance optimizations become possible. For example, many systems will cluster or group a number of pages and write them out at once to the swap partition. Again, for example, many systems will cluster or group a number of pages and write them out at once to the swap partition. So many daemons do this. It will group first the pages and then write out, thus doing the I/O at once. Thus increasing the efficiency of the disk, as we will see later when we discuss disk in more details. Such clustering reduces seek and rotational overheads of a disk and thus increases performance noticeably. To work with background paging thread, the control flow in figure 21.3 should be modified slightly. So these are the new algorithm for the OS. Instead of performing a replacement directly, the algorithm would instead simply check if there are any free pages available. If not, it would inform the background paging thread that pages are needed. When the thread frees up some pages, it would reawaken the original thread. Again, if not, it would inform the background paging thread that the pages are needed. When the thread freed up some pages, it would reawaken the original thread. So it will run this first at once, and then after it free up some space, it will now call the original thread or the original process, which could then page in the desired page and go about its work. So that original thread will now page in the desired page from disk to memory and go about its work. So here pfn find freeze page, find a free physical page. If pfn equal -1, no free page found. Pfn equals evict page, replacement algorithm. Think I got this. I think I got this diagram wrong. Just a moment. Yeah, it's still the same, but basically, instead of performing a replacement directly, the algorithm would instead check if there are any free pages available. So if there is pages available, so if not, we will have an if here. If not, it would inform the background paging thread. So if not, inform the something like that, the background pages. And then when the thread frees up or finishes up, background thread finishes up freeing up space, it would then reawaken the original thread, which would then page in the desired page from disk to memory to go about its work. So that will be the new algorithm, and it updates the page table present and then retry instruction. So it's still the same, but you're just clustering this sleep wait for IO, and it check first for free pages. So it constantly check for free pages. So this can be useful for some cases, but for some cases you could use replacement policy code, which we will discuss further in the next chapter. So in this brief chapter, we have introduced the notion of accessing more memory than it's physically present within a system. To do so requires more complexity in page table structures, as present bit of some kind must be included to tell us whether the page is present in memory or not. When not, the operating system page fault handler runs to service the page fault, and thus arranges for the transfer of the desired page from disk to memory, perhaps first replacing some pages in memory to make room for those soon to be swapped in. Recall, importantly and amazingly, that these actions take place transparently in the process, As far as the process is concerned, it's just accessing its own private contiguous virtual memory. Behind the scenes, pages are placed in arbitrary, non-contiguous locations in physical memory, and sometimes they are not even present in memory, requiring a fetch from disk. So sometimes this paging is not contiguous in memory. Some program is not, but some program really requires like accessing contiguous memory, such as like your USB devices or anything that you input. So those are requires contiguous memory. But a lot of programs does this. You may think that once you access a program, it's contiguous in your disk and memory. No, though it is transparent, it may not be contiguous at all when you're accessing it. While we hope that in the common case a memory access is fast, in some cases it will take multiple disk operations to service it. Something as simple as performing a single instruction can, in the worst case, take milliseconds to complete. So, again, sorry, I think I have not mentioned this. So, if you're the reason why we're doing this page fault from disk to memory is because as the operation of this could be 10,000 to 100 times slower than running it in memory or in TLB. So while we hope that in the common case a memory is fast, in some cases it will take multiple disk operations to service it. Something as simple as performing a single instruction on can, in the worst case, take milliseconds to complete.